I'd like to go through rational inequalities and give you a couple of examples. But I also need to give you a bit of context because it's worth your while understanding sort of what's going on, as well as just purely the sort of algorithmic process that you would do algebraically. So rational means sort of a ratio, means a fraction. Okay, so you can see here we've got an algebraic expression that is a fraction. We say rational expression, and it is in an inequality. It's greater than or equal to 1. So before I'm actually going to show you the process of finding a solution to this question, it's worth your while understanding what's happening with that left-hand side. I'm going to show you a graph of 2x minus 1 over x plus 1 as a function. Okay, so you can see the green curve there. There's two parts to it. Okay, this is what f of x equals 2x minus 1 all divided by x plus 1 would actually look like. And I'm going to briefly comment on sort of the key features. You'll notice that there's sort of two parts to it. Okay, there's a top part on the left-hand side, and there's another part to the bottom right-hand side, and they don't seem to be connected. And in fact, we have what's called asymptotes, which is, you've got a blue one here, x equals to minus 1, another one which is y equals 2. And the reason for this is this is where, for example, in the domain, you can't have x equaling to minus 1, because you'll see with the expression, if you put minus 1 into the denominator, you'd get 0, and you can't divide by 0. So x equal to minus 1 is not an option for the domain values. You can't put it into that function. Likewise, the red line, the horizontal red line, y equals 2, represents the fact that you can't get 2 out as an answer. So 2 is not going to be part of the range. It's not actually even possible to be part of the codomain. It's just not going to come out as an answer. Okay, what actually happens is as x increases to an infinitely large number, when you're putting a large number into the expression 2x minus 1 all over x plus 1, you're going to end up with an answer that gets closer and closer and closer to, but never actually gets there. So that's what the graph actually looks like. But in terms of us actually solving the inequality, we don't need to worry about that function, because there's a process we can go through that converts it into a quadratic and then allows us a fairly straightforward process of finding the solutions to the question. Now, I'm just going to give you the answer graphically first, actually, before we even do the algebra, because if you were to have the graph well drawn, and if you were then also to look at the section that is greater than 1, you'd end up with the shaded area. So basically from 2, 1, okay, and beyond, okay, so for values of greater than 2, we have the graph being greater than 1. It's above that blue line. Likewise, you'll see on the other section of the curve, you can see here that this section here is above the inequality line, and so all the values from negative infinity down to, but not including minus 1, will also be part of the solution. So we're going to see how to get that in a fairly straightforward algebraic sort of process without actually having to worry about what the graph looks like and worrying about where the asymptotes are and so forth. So the other bit of information that you need to be reminded of is the fact that with an inequality, you should not or must not multiply the inequality by a negative, i.e. you mustn't multiply both sides by a negative or divide by a negative in order to try and simplify the expression. So, because usually if you have an expression with a denominator, the first thing you want to do is multiply that out. Okay, do the opposite of division and multiply it out. The problem is that x plus 1 as an expression could be negative. If x is anything, minus 2, minus 3, minus 4, if you put any of those numbers into that denominator, you get a negative. So we're not allowed to just multiply out by the denominator. So what we have to do instead is we have to multiply both sides by the square of the denominator. And the reason for this is because that anything that's squared, that's real, okay, will give you a positive value. So if we now multiply both sides by the square of the denominator, we're definitely multiplying both sides by a positive expression. So for this question, we're going to find that when we're multiplying both sides by the square of the denominator, you're going to have a bit of cancelling going on. So effectively, what we're actually dealing with is x plus 1 multiplied by 2x minus 1 on the left-hand side. On the right-hand side, we've got 1 multiplied by x plus 1, x plus 1. That's what's actually going on. So let's multiply it out. And once we've tied it up and equaled it to, or not equaled it, but have 0 on one side of the inequality, we end up with x squared minus x minus 2. So basically, we've converted a rational inequality into a quadratic inequality by multiplying both sides by the square of the denominator. Now it's the same as any other question you might do with a quadratic inequality. We're going to factorize to find the critical values and be able to decide, using those critical values, what is the range of values that would fit the inequality. So if we were to factorize this, I would get a factorized version, which is x minus 2 multiplied by x plus 1, also greater than 0. And the critical values we're interested in is the solution suite to those factors equal to 0, which is x is equal to 2 and x is equal to minus 1. So we know these are important in terms of our boundaries. So let's have a little quick sketch of, so now we're going to do a quick sketch of the quadratic, this quadratic, not having to worry about that rational expression. So if we think about our function, we have critical values of minus 1 and 2. So you'd have a curve if you were to draw this. Okay, this is a very quick sketch. Okay, the key feature here is that when is the function greater than 0? Okay, it's going to be greater than 0 in these sections here. It's above the x-axis, and so the values of x that would meet that criteria would be anything that's greater than 2 or less than minus 1. So x is going to be greater than 2 or it's going to be less than minus 1. So that's the solution of the original inequality. And just to go back to that inequality, you'll see here's the example of x being equal to 2. And any x value greater than 2 gives us the curve greater than 1, and likewise anything less than minus 1. Okay, any x value less than minus 1 gives us the curve greater than 1. So there's the connection with the original function. So I'll go through another question. I'll go a bit faster with a little less explanation. So we have 3x minus 2 all divided by 2x minus 1, and that is less than 5. So again, we have a rational expression in an inequality. So again, you multiply both sides by the square of the denominator, which when we cancel out the denominator gives us 2x minus 1 multiplied by 3x minus 2 is less than 5 multiplied by 2x minus 1, 2x minus 1. And when we expand those brackets, we end up with 6x squared minus 7x plus 2 is less than 20x squared minus 20x plus 5. And if we make that all so 0, not equal to 0, but with an inequality with 0, it's best to put everything on the right-hand side to ensure that the x squared term is positive, and we get 14x squared minus 13x plus 3. If I were then to factorize that, I would end up with the following. I'd end up with 7x minus 3, 2x minus 1 as the two factors. So we now want to sort of solve that as such to be able to get the critical values. So we end up with x being equal to 3/7, or we have x being equal to a half. So they're my two critical values, 3/7 and a half. So now I have to think about, what is going on with this graph. So again, this is quadratic. It's greater than 0. So again, if I think about my my curve, there's 3/7, there's a half, and so my curve is doing something like this. It's coming down and back up again. There's 3. It's not very to scale, doesn't matter. The key idea I want to appreciate is when is my curve greater than 0. So again, similar to my last example, we're talking about this section here and this section here. So therefore, my solution to the question would be x has to be less than 3/7, or it has to be x is greater than a half. Okay, so it's in a sense it's all the values for x in those boundaries. Just to remind you that if you had it the other way around, if the quadratic positive quadratic was less than 0, you'd be concerned about the section in between. Okay, and so therefore, so for this question here, if the inequality had been the other way around, okay, you would have had an inequality answer that would be written in that double-ended format. Okay, so that's just an alternative, since I didn't go through an example that showed that. Okay, so you should be able to have a go at the questions from exercise 12.2, questions 9, 10, 11, 12, if you wish. Just and you can stop watching this video now. However, just for anyone who's interested, I'm just going to go through an alternative method, okay? One that's peddled by quite a lot of people. I'm quite happy with what I've shown you so far, but you might be interested in an alternative approach. So this involves you appreciating the idea of, when you're adding, when you're multiplying and dividing by a positive or negative. So a positive divided by a positive gives you a positive answer. A positive divided by a negative gives you a negative answer, and so on and so forth. You would have learnt that in first year. And we can use those ideas here especially if we rearrange this inequality slightly so that it has 0 on the other side. So I'm going to take away 1 from both sides, and I want to make a single fraction, okay, a single denominator. So when I am subtracting x plus 1, okay, 1 lot of all over x plus 1, and I tidy that up, I end up with x minus 2 all divided by x plus 1, and that is greater than 0. So what I have is a rational expression that is greater than or less than 0. So I can now think about is basically, can I get an expression that is positive? That's what we're talking about here. So the left-hand side is going to be greater than 0 or equal to 0. It's going to be positive. So how can I get this expression to be positive? I can get it positive if both the top and the bottom are positive, and I also look at other scenarios such as both top and bottom are negative. So to do this, I need to appreciate the critical values, and you can see here that this is an expression is equal to 0. The numerator here is equal to 0 when x is equal to 2, and we can also see that the denominator, when the denominator is equal to 0, x is equal to minus 1. So I'm going to pull those two values out as my critical values. And so I understand that, if x is greater than 2, then the top is positive. Okay, if x is less than 2 here, then this numerator will be negative. So what I end up looking at is values up to minus 1, values between minus 1 and 2, and values above 2. So when the value of x is less than -1, what can I say about the numerator here, x minus 2? Well, if I put anything less than -1 into this expression, it's going to be negative. Okay. If I put a number between -1 and 2 into there, it'll also be negative. And lastly, if I were to put a number that's greater than 2, okay, into this expression, I'd end up with a positive value. So I'll do the same process with the denominator, the x plus 1. So if I put any number less than -1 into this, I get a negative value. If I put a number that's between -1 and 2, and by the way, when you're doing this, you could just pick a number between. So if I put 0, okay, so that's, into there, what do I get? I get a positive answer. Okay, so you don't need to. You can actually use examples, numbers that are actually in those boundaries, to be able to understand what the expression is going to be. And lastly, if a value of greater than 2 goes into here, it'll also be positive. So when I'm doing a division, so when I'm doing a negative divided by a negative, okay, what we're getting is this scenario here, where my answer will be positive. It'll be greater than 0. If I were to look at values between -1 and 2, okay, I have a negative divided by a positive. That is going to give me this scenario here, which gives a result that's negative. And lastly, the division of a positive divided by a positive will be, using the same logic, will be positive. So what we have there is a situation where the boundaries of less than -1 or greater than 2 will give me a number that is greater than 0. So my solution to this question is, as written, x is less than -1 or x is greater than 2. And if you want to look at this method a bit more, I would say actually you could find a variety of different videos online on YouTube that would give you further examples of this idea of looking at the polarities inside the rational expression. I would still hold that the first method I went through is probably a more sort of clinical method that uses what you know already.